this is section 19.7 and it's about the Nernst equation and concentration cells. So the section is about these two related topics, but in this opportunity we are going to focus our attention only on the Nernst equation. Okay, so we are going to leave the concentration cells out of the discussion, just so you know, which is going to make your life a little easier, right? So the Nernst equation is simply an equation that we can use to calculate the potential for any given electrochemical cell under conditions that are different from standard. So up to this point we've been working with those potentials, but that implies that we've been working at concentrations that are 1 molar, you are at 1 atmosphere of pressure, and well, temperature 298. We're gonna keep working at 298 for Kelvin for that matter. But I want you to recall that back when we were working with equilibrium, we had this equation. If you were to calculate delta G for any given reaction at conditions different from standard conditions, then you use this equation. Remember, Q is basically the ratio of concentrations, whatever they are. Okay, so not necessarily you have to be under equilibrium conditions. So any concentration that you have at any point in the reaction, then that's Q. And here temperature, well, you can change temperature for whatever you need. So standard conditions still would be 298 Kelvin, but if you're working out of that range, you can change the temperature using this equation. Now, another thing to remember here, delta G with the degree symbol, if you will, that is under standard conditions. So you still need the value from standard conditions to calculate delta G at different conditions. So that's kind of your starting point. And the same is true if you are working with potentials. Now, based on what we've covered so far, we have that the potential of any given cell is related to the delta G for that reaction through this equation, right? So, and the same is true for delta G at a different condition. So we can actually say that delta G, that means delta G at any other condition, it's going to be equal to minus n. N is the number of electrons being transferred. F is the Faraday constant, and here is going to be your potential at those conditions. Okay, but they are pretty much the same. So we can actually take these two equations and incorporate them in the one that we have on top. So if we replace delta G with the corresponding expression, we will have minus NFE is going to be equal to minus NFE standard plus RT logarithm of Q. Okay, but what we're gonna do now is we are going to divide all this. Okay, both sides of the equation, we are going to divide that by minus NF. Okay, the whole thing minus ANF. And the result here is that we are going to cancel this with this with this, and well, now this sign becomes a negative sign, and what we end up with is with the equation that we are going to actually use here. Okay, the potential for any given electrochemical cell at conditions different from standard is going to be equal to your standard potential minus, remember that minus comes from that multiplication there, minus RT divided by NF times the logarithm, the natural logarithm of Q. Alright, you can make your life a little easier if you take this equation and use it in this form. E is equal to E standard minus 0.0592 divided by N logarithm of Q. Okay, so this is natural logarithm. That doesn't read good, does it? This is your natural logarithm, and this is your base 10 logarithm. Since you've been working with pH and using base 10 logarithm, I mean, this implies, this equation right here implies that you have to do, or you have to put less numbers on your calculator. Okay, because if not, then you will have to be multiplying R times T times F on top of everything else. So it's up to you how you're gonna use it. Either way, you're gonna have the same answer. Okay, so for the most part, I probably be using the full equation. So we have this reaction here, and this we are working with just one half reaction, and this is zinc 2 plus. Since we want to see this from the point of view of a reduction potential, so we have zinc 2 plus 2 electrons goes to zinc solid. So this is your reduction reaction for that half cell. Okay, remember, your standard reduction potentials are always from the point of view of a reduction. Here there are 2 electrons, so N in that equation, this N right there is equal to 2, right? And now we want to calculate, for this particular reaction, the standard potential is equal to minus 0.76. Remember, these are volts. But if you want to calculate the standard the potential of this half reaction when the concentration is 0.1, remember, standard is 1 molar, but if you now have a solution with 0.1 molar zinc, then we have to calculate the potential of that cell, and to do so we have to calculate Q. Now, what's Q in this particular reaction? We have a solid and we have something in solution, right? So we are going to, it's technically this you could treat this as a equilibrium reaction, which means if you are going to calculate Q, is the same thing as if you were calculating the constant for this reaction. And in order to do so, is product minus reactants. But in the product side, you have a solid, so that is going to be 1 divided by the concentration of your zinc 2 plus. Okay, so this is Q for this half reaction. All right, and that means that if the concentration is 0.1, then Q is going to be equal to 1 divided by 0.1, and that is equal to 10. So this is the value of Q. Now, if we use our word equation, we have that E is equal to standard potential minus RT and F logarithm of Q. All right, this whole thing is going to be the potential, the standard potential, which is minus 0.76, and we are going to subtract the fraction that you obtain when you multiply 8.314 times 298 divided by 2, because it's the number of electrons, times the Faraday constant 96,485. Trust me, the whole, if you do, as long as you use your 8.314, 298 and 96 here, the units of that whole fraction here is volts. Okay, because logarithm of 10, it has no units, so this whole term here, the units that you obtain there is volts. And when you complete this operation, you will obtain minus 0.79 volts. So for that particular half cell, when the concentration of zinc 2 plus is 0.1 and not 1 molar, the potential of that half cell is going to be minus 0.79 volts. Okay, it becomes a little more negative than what you had initially. All right, so what if now we combine this with another reaction? right? Another half reaction, so that we have a full cell. Now we have a cell that contains zinc and silver. So what are the reactions here that we are looking at? So we have the same that we had before, zinc 2 plus 2 electrons, they go to zinc solid. And if it's silver, then silver is Ag plus 1 electron that goes to silver solid. Okay? How do you know that they are solids? Well, you have a zinc electrode immersed in a 0.1 molar zinc solution, and you have a silver electrode submerged in a 0.5 molar silver nitrate. Okay, so what is the overall reaction here? So if the potential of this cell is minus 0.76 and the potential of this cell is plus 0.80, okay, so this is the actual reduction reaction, and this will happen as an oxidation reaction. Okay, so you are reducing silver and you are oxidizing zinc, the solid. Okay, so your overall reaction is actually, and notice that we have to, this reaction has to be multiplied by 2 so that you have the same number of electrons. Okay, so actually your reaction is zinc solid plus 2 silver ions going to zinc 2 plus let's put it plus 2 silver solid. That is your reaction. Now I want you to notice here that the things that you have in solution are the silver ions and your zinc. Okay, and the zinc is your product. So here Q is going to be the concentration of zinc divided by the concentration of silver, and you have a stoichiometric factor of 2 here, so silver has to be raised to the power of 2. Okay, and this is the concentration of zinc is equal to 0.100 and the concentration of silver is 0.100, and we raise that to the power of 2. That means Q here is equal to 0.400. Alright, so what is the potential? What is the standard potential in this cell? The standard potential in this cell is cathode minus anode, correct? So this is your cathode, this is your anode. Okay, so the standard potential for this cell is going to be plus 0.80 minus 0.76. Okay, and this is equal to 156 volts. Okay, we have our starter potential, so this is one part of the puzzle, this is the other part of the puzzle, and now let's connect the pieces together. Well, actually 2 electrons is the other part of the puzzle, so it's time to connect all these pieces together. So your potential, remember the equation is this one right here, right? So your potential is going to be 156 minus 8314 times 298 divided by 2 times 96,485 times the logarithm of Q, which is this number here, 0.400. Okay, so just in case you are, it's hard for you to follow me, how about we do this? This is R, this is T, this is N, this is F, and this is Q. Okay, so you end up with a potential under those conditions that is equal to 157. Not much change actually. Okay, it's the combination of concentrations, but it's a little bit different from your initial potential. So how about we make more drastic changes here? Okay, so now we have this cell. Now this cell is using iron and magnesium. Okay, we have the reaction right there, and you are to calculate the potential for this cell under 3 different conditions. Number 1, standard conditions. Number 2, when the concentration of iron is 1 10 to the negative 3 and the concentration of magnesium is 2.50 molar. And number 3, when the concentration of iron is 2 molar and the concentration of magnesium is 1.5 10 to the negative 3. So let's take care of the first one, right? So if we take our reactions, so the first one is actually, if we look at them from the point of view of a reductions, then we have iron plus 3 electrons going to iron solid, and the potential for this half reaction is equal to minus 0.04. For magnesium, the reaction is magnesium 2 plus 2 electrons going to magnesium solid, and the potential for this half reaction is minus 237. Therefore, the reaction with the more positive value will happen as a reduction, and the reaction with the most negative potential will happen as an oxidation. Okay, so that's why you are actually oxidizing magnesium in that reaction. All right, so our standard potential for the cell is going to be equal to minus 0.04 minus 237 volts, and this is equal to 233 plus 233 volts. Things that I want to take care of before we move on. Okay, we need to, since we are going to calculate these at different conditions, you need to know the number of electrons that are being transferred, and that number of electrons have to be the same for both half reactions. In order to accomplish that, then you have 2 electrons here, right, and 3 electrons there. So the easiest way to do this is to multiply the first equation by 2, the second equation by 3, and that's why you see those stoichiometric coefficients there. Okay, so therefore out of these you get to the conclusion that N is equal to 6. There are 6 electrons being transferred between the reactants in this reaction. All right, but we got our potential. Out of this information, we got the standard potential and we got the value of N. Right, so let's move on to the next case. Right, so let's write that down. Interesting. Okay, let's keep it here. So the potential was plus 233 and N is equal to 6. All right. So now we have our reaction, so no need to worry about that, about the sort of balancing that we were trying to do. You have 2 solids here in this reaction, iron solid and magnesium solid, so you don't consider them at the moment of calculating Q. So Q for this case is going to be the concentration of magnesium 2 plus raised to the power of 3 divided by the concentration of iron 3 plus raised to the power of 2. Okay, what are our concentrations here? So we have that magnesium is 250 molar, and we're raising that to the power of 3. And for iron, the concentration is 1 10 to the negative 3, and we're raising that to the power of 2. So out of this, we get that Q is equal to 156 10 to the 7th. Okay, it's a really large number, right? So if our equation is E equal E0 minus RT NF logarithm of Q, then our potential here is equal to the one that we have already calculated plus 233 minus 8314 times 298. Now we have 6 electrons times 96,485, and we multiply that by the logarithm of 156 10 to the 7th. And what we get out of here is 226 volts, positive 226 volts. So now we have a more significant change here. Still, you might consider that it's small, but more significant than in the previous case. Okay, so this is when the concentrations of magnesium and iron are like that, then the potential of your cell changed to plus 226 volts. Now, what if we go the other way around? What if we have a larger concentration of iron and a smaller concentration of magnesium? So the data that we were using before in terms of the standard potential is still the same, plus 233. There are still 6 electrons being transferred, but now we have to recalculate Q because now we have different concentrations. So Q is equal to magnesium 2 plus cubed iron 3 plus squared, and this is equal to 1.5 10 to the negative 3 raised to the power of 3 divided by 2 squared. Q in this case is now 844 10 to the negative 10. So it's a much smaller number now. And now if we calculate the potential is plus 233 minus, same thing, 8314 298 696,485. I want you to notice that these numbers actually never change in this calculation. This is the only one that is gonna change because the different reactions, different number of electron transfers, but the constant is gonna, this is a constant, this is a constant, so they will not change. For the most part, we're gonna be working at the same temperature, so you can do those that calculation in advance and having as your own equation. Now here is the logarithm of 844 10 to the negative 10, and the potential that we obtain here is equal to plus 242 volts. Okay, so in the previous case the potential was a little lower than the standard potential. In this case the potential is a little higher than the initial potential. Okay, in every single case the reaction is still spontaneous because you are obtaining a positive potential. Okay, so there might be cases in which the concentrations are such that you will have a reverse potential and then the reaction becomes non-spontaneous, but in this particular case it's not gonna happen. All right.